blistering burst of X-rays which hit the Earth, and then it would scorch all plant life. And with the collapse of the food chain, we're talking about a possible extinction on the Earth.
Supernovas are killers. But they also create the basic elements that make up our world.
Our planet, our star, everything around us formed out of the debris of a dead, exploded star. Everything that makes up our bodies and the skyline came from supernovae. All of the iron, all of the silicon, all of the elements that went into these buildings. The things that make up my blood, my body, the gold in my wedding ring. Everything you see here is a supernova.
But our sun won't become a supernova. It's too small. Like all stars, it's basically a giant nuclear reactor. The fusion reactor inside a star burns hydrogen, the simplest, most common element. The reaction fuses hydrogen atoms together, producing helium and energy. And when the hydrogen runs out, stars keep burning by fusing helium into carbon, then carbon into oxygen. When small stars like our sun make carbon, they begin to die.
During the lifetime of a star, there's a balance between gravity pulling in and pressure pushing out. For a star that's generating energy, there's no problem. But once energy generation switches off, the pressure goes away and gravity wins.
Now, gravity begins to crush the center of the star. The star's outer layers are pushed outwards. They expand into a huge ball of gas called a red giant.
Our sun, when it dies 4.5 to 5 billion years from now, its corona will go all the way out to Mars. Everything on the planet Earth will vaporize.
While the outer layers expand, in the center of the sun, gravity will have the opposite effect. It'll crush the sun's core to just a millionth of its original size, about the size of the Earth. Now, it's a dense ball of oxygen and carbon called a white dwarf. In our solar system, this will be the end of the story. The gas from the dying star will gradually disperse, but the tiny white dwarf will burn for billions of years. But our solar system is unusual. It has just one star. The fact is, the vast majority of stars orbit in pairs. When one of the two stars dies and becomes a white dwarf, if it's close enough, it starts stealing material from the other star.
Think of two stars rotating around each other. One star slowly sucking all the hydrogen and helium from its companion star. It's like a vampire.
As the white dwarf sucks more and more fuel out of its companion star, it gets heavier and denser and less stable. Inside, carbon and oxygen atoms are about to fuse together, and that's bad news.
A white dwarf, in some sense, is like a bomb waiting to be lit. There's a huge amount of energy stored in that star, gravitational energy and nuclear energy.
This white dwarf is turning into a monster, a Type 1A monster.
A Type 1A supernova is a 20 billion megaton thermonuclear carbon bomb.
It's one of the most explosive substances in the universe.
Eventually, the white dwarf drains so much material from its companion it goes into nuclear overload. The carbon and oxygen inside it start to turn into a common but dangerous element, at least to stars.
You've probably seen in Star Trek the idea that there's some sort of secret technology that kills a star. Well, I mean, it's in your frying pan that you used this morning for breakfast, iron.
The moment the white dwarf star starts to fuse carbon and oxygen into iron, it's doomed. Suddenly, the white dwarf explodes.
The nuclear explosion of a white dwarf include, among other things, huge amounts of iron. And in fact, Type 1a supernovae are of vital importance to populating the universe with the kind of elements that are important to us.
Type 1a supernovas blast iron trillions of miles into space. It's where most of the iron in the cosmos comes from. But what about all the elements that are heavier than iron, like gold and silver? Where do they come from? The answer again is other stars. Single stars, bigger stars. Supernovas make everything in the universe. Everything we see, all the material in planet Earth, was created inside a supernova. Even you and I are made from dying stars.
Without supernovae, we wouldn't be here. Every atom in your body was once inside a star that exploded. And the atoms in your left hand may have come from a different star than the atoms in your right hand. You are literally stardust.
Almost all of the iron in our solar system came from a double-star supernova that exploded more than 5 billion years ago. From our planet's molten core, to our skyscrapers, to the hemoglobin in our blood, it's all made of iron from Type 1a supernovas. But the heavier elements in our world, like gold, silver, and uranium, come from another type of supernova. A single-star supernova. This is our sun. A single star has to weigh much more than our sun to go supernova. And there are some monster stars out there. Some are dozens of times heavier than our sun. And some are hundreds of times more massive. The heavier the star, the faster it burns. And when these massive stars begin to age and die, the nuclear reactions inside them speed up.
Giant stars burn through their nuclear fuel very, very fast. It's sort of the live fast, die young. The more mass a star has, the hotter it burns inside, the faster it burns through its fuel.
Unlike double-star supernovas, really massive single stars create lots of elements before they explode. Once they turn hydrogen into helium, helium into carbon, and carbon into oxygen, they don't collapse into white dwarf stars. Instead, giant stars keep on burning, building up layer after layer of new elements deep in their core.
Big stars don't stop after they've burned helium to carbon and oxygen. They go ahead and burn carbon to still heavier elements, and then neon and oxygen to silicon, until you get this nested Russian doll spherical layer cake kind of thing.
These elements are the building blocks of the universe. But they're trapped inside the giant star. Somehow, they've got to get out.
Studying exploding stars has taught us how the heavy elements of the universe came to be. They were formed by nuclear reactions inside stars. But if some of those stars were not to explode, then those elements would be locked up forever.
The trigger that'll release the elements in the single giant star is the same element that causes the Type 1a supernova to blow up: iron. Iron eats up all the energy of the star's nuclear fusion. Without the energy from nuclear fusion pushing out, gravity begins to crush down. The big star is doomed.
The last moments of a star are really phenomenal. The star might last for 10 million years on the way to becoming a supernova, but the last little bit takes place very rapidly. Once you have an iron core and once it gets out of balance, it collapses in a thousandth of a second, a millisecond, from the size of the Earth down to the size of Manhattan. It's traveling about 1/3 of the speed of light as it crunches down.
As the star becomes unstable, the massive power of gravity causes the core to collapse. This happens with such incredible power, even the atoms inside start to crush together. As it gets smaller and denser, the core builds up more and more energy.
It's something with about 1.5 times the mass of the sun that has collapsed to something that's only about 15 miles across. It's got incredible density. You know, it's 1,000 trillion times the density of water.
Now, the star explodes. The blast rips through the star's outer layers, and in the process, makes all the elements heavier than iron. Iron becomes cobalt. Cobalt becomes nickel. And on to gold, platinum, and uranium. The explosion is so brief, it only makes small amounts of these heavier elements, which is why they're so rare. The supernova blasts these new elements billions of miles into space.
The only method we know, the only mechanism that we have found anywhere in the universe for creating new elements is in the death throes of a star called a supernova.
It seems incredible that anything could survive a supernova explosion. But we now know that some of the biggest bangs in the universe leave a corpse behind. And these are some of the strangest and most deadly objects ever discovered. When a giant star goes supernova and explodes, it's not always the end. Sometimes there's a corpse. What kind of corpse depends on the size of the star. Supernovas from stars more than 8 times bigger than our sun leave behind a neutron star, and it's one of the strangest objects in the universe.
These things you can almost think of as sort of the zombies of the stellar world. They're very dangerous, they're very weird, and stars make them all the time. They're all around us.
As a giant star goes supernova, the core is crushed from the size of a planet to the size of a city. The pressure in the core is so intense, even the atoms inside it are crushed together. When the atoms are packed that tightly and there's no space left between them, the massive energy buildup means something's got to give. The core blasts off the outer layers of the star. And what remains is a super-dense neutron star.
A neutron star has the mass of a star crunched into a very small volume. And that means the density is incredibly high.
Well, imagine taking the Empire State Building here behind me, crushing it into the size of a grain of sand. That's the density of the entire neutron star. So if you had something that dense, if you dropped it, it would fall straight through the Earth, just like a hot knife through butter.
A teaspoon of neutron star would weigh 100 million tons. Imagine something as heavy as a star, but only the size of New York City. And it's spinning.
Some of them may be born rotating 1,000 times a second. I mean, think about it. Something 1.5 times the mass of the sun going around 1,000 times a second.
Some neutron stars spin so fast, they generate huge pulses of energy. Beams of radiation blasting out of the star's north and south poles. This neutron star is called a pulsar.
There's one of these things in the center of the Crab Nebula, the place where there was a supernova explosion about 1,000 years ago. And it's one of the fastest spinning of these objects.
This is the actual sound a pulsar makes, recorded by radio telescope. It will flash 30 times a second for millions of years. But pulsars aren't the strangest thing a supernova can leave behind. When stars 30 times bigger than our sun explode, they produce a type of neutron star called a magnetar. Magnetars are even weirder than pulsars and generate powerful magnetic fields.
Now, in the most extreme case, the magnetic field can be 10 to the 15, 100 trillion times the magnetic field of the Earth.
That's so strong, it would suck the iron right out of your blood from thousands of miles away. But even pulsars and magnetars aren't the most dangerous objects a supernova can leave behind. When the core of a supermassive star collapses, it doesn't just crush atoms. It crushes space and time itself. And that is when a supernova creates a black hole. When stars over 100 times heavier than our sun explode, they make a supernova explosion so big, scientists call them hypernovas. And it was a hypernova that almost started World War III. In 1963, the US and Soviet Union agreed to ban testing nuclear weapons. To keep tabs on the Russians, the US launched spy satellites. When they heard this sound coming from deep space, they suspected the worst.
The United States government launched the Vela satellite, looking for nuclear detonations. And then, looking in outer space, they saw these monster explosions take place. And the military thought, oh my God, the Russians are testing secret atomic weapons in space.
But these weren't secret atomic bomb tests, and the Russians had nothing to do with them.
They began to look at where this radiation came from. It came from all over the galaxy, beyond the galaxy. Now, there's no way the Russians could shoot explosions in outer space beyond the galaxy. And then people began to realize that we were staring something new in the face.
They were super powerful explosions of high-energy radiation called gamma-ray bursts. The question was, where did they come from? The answer was exploding hypernovas. During a regular supernova explosion, gravity crushes a star's core into a neutron star. But during a hypernova explosion, the giant star is so much bigger that gravity crushes the core into something much stranger. black hole. And the black hole immediately begins to devour the dying star around it.
The rest of the star can't all go in that little bitty hole in the middle. It starts to swirl around and it forms an accretion disk, which is feeding the black hole at about 1 million Earth masses a second. And so, as you might imagine, something dramatic is going to happen here.
1 million Earth masses a second is too much for the black hole to consume all at once. So it spits a lot of it back out at nearly the speed of light. This creates two beams of pure energy blasting their way out of the black hole.
It takes it about 8 seconds to bore through the star, keeping a very tight focus, and erupt from the surface. Now, if we're standing in the opening of this jet, we'll see a gamma ray burst.
The gamma rays produced from the black hole tear through the outer layers of the star and into space.
Gamma ray bursts are the most violent event that we know of in the universe. A giant star blows itself to pieces and forms a black hole. It's incredibly spectacular.
These gamma ray bursts are so energetic, they light up the entire universe. Any point in the universe will eventually pick up this astounding radiation coming from a gamma ray burst. That's how energetic they are.
They are the brightest things in the known universe.
To put things in perspective, a typical supernova explosion is about what the sun will put out in its entire 10 billion year lifetime. A gamma ray burst, viewed jet on, is 100 million times more luminous than a supernova. They're the champions for brightness, for sure.
They're not only bright, they're lethal. If a gamma ray burst were to hit the Earth, it would destroy most of the atmosphere in seconds.
A gamma ray burster is like a rifle shot. And if you're in the line of sight, watch out. Once the radiation hits you, it'll bathe the entire surface of the Earth with nitric oxides, which will wipe out the ozone layer. Blistering radiation would hit plant life, hit algae. The whole food chain would collapse.
If the burst was close enough, it would cause mass extinctions.
Gamma ray bursts turn out to be a lot more common than we thought they would be. So it's possible that some of these have even hit the Earth in the past. That's a pretty scary scenario. It may already have happened.
The question is, if it happened before, could it happen again?
A gamma ray burster is basically a supernova on steroids. You need a giant star to die violently. Now, the nearest star to us that might do that is Eta Carina, and it's a spectacular nebula. There's all kinds of material flying off the star. It's very unstable. It may already have exploded in a gamma ray burst.
But Eta Carinae may not be the only threat. There are other dying stars out there.
Believe it or not, one of them is pointed in our direction. We are staring down the gun barrel of WR-104, two dying stars that will one day undergo a gamma ray burst. Not a question of if, a question of when. That WR-104 may have our name on it.
But the good news is we probably wouldn't know about it in advance. The shock would hit us before we had a chance to do anything. So there's no sense worrying about it anyway.
The truth is, we'll never know if a star is about to go hypernova and explode. Anyway, by the time we see it, it'll already be too late. In fact, we're already exposed to rays from dying stars every second of every day. When giant stars explode, they make the biggest bangs in the universe. But what gives them so much punch? Until recently, no one knew.
Scientists, when they tried to simulate a supernova explosion in a computer, had a problem. They simply could not get enough energy out of the dying star to create a supernova. This was a calamity in astronomy.
Computer models couldn't make the simulated stars blow up. To blow up a star, you need a lot of energy. The trouble was, astronomers couldn't find it.
The visible radiation that you see is a tiny fraction of the total energy emitted. Even the energy of motion of the expanding gases is only 1% of the total energy.
Where was the missing 99% of the energy from the explosion? The only way scientists could get their simulations to match the real thing was to add in a mysterious particle called the neutrino. Without it, their numbers didn't add up. That was the easy bit. Their next step was to prove supernovas really do produce neutrinos. In 1987, they got lucky. 168,000 years ago, a supernova exploded in a nearby galaxy called the Large Magellanic Cloud. When scientists saw the light from the blast, they called it Supernova 1987.
Supernova 1987A is really important in the study of supernovae because it's the first one since the invention of the telescope. It's the one that we've been able to study right from the time of explosion through now using all the instruments that we've developed.
One of those instruments was a giant neutrino detector buried deep underground.
And bingo, we saw a burst of radiation go through our neutrino detectors, and we said, aha, that's the proof.
The discovery of neutrinos from Supernova 1987A was a tremendous thing because for many years, people had been saying that's where 99% of the energy goes, but no one had ever seen it.
This is now the smoking gun that we can now prove that neutrinos carry the energy of a supernova, and we detected it right on the Earth as we saw a supernova in outer space.
Neutrinos are trillions of times smaller than atoms. They're created by all sorts of nuclear reactions, from nuclear power plants and bombs to exploding stars. If you had neutrino vision, you'd see them everywhere.
Neutrinos are ghost-like particles. Literally trillions of them are going through my body even as we speak. In fact, neutrinos come from the bottom of the floor, right through the Earth, and even hit me right through my legs.
Pretty strange. Imagine so many tiny particles zooming through our bodies. But where do they get all their energy? When a core crushes down just before a supernova explosion, the atoms inside it are broken up. The core gets so hot, it turns this atomic debris into blazing neutrinos.
We think that supernovae produce a stupendous sum of neutrinos when the core collapses to a neutron star. For about 10 seconds, that core shines with a neutrino luminosity that is greater than all of the energy being produced in the rest of the universe at that time.
In other words, it's really bright. But gravity can't hold these neutrinos in the core. They burst free in a blinding flash of light that rips the dying star apart. The discovery of neutrinos transformed the science of supernovas. But supernovas were about to reveal the most mysterious force of all, one that's changing the destiny of the universe. Supernova explosions are so bright, we can see them across the entire universe. This has helped astronomers unlock one of the deepest mysteries of the cosmos. The universe came to life in the Big Bang 14 billion years ago. It expanded from a tiny ball of energy, smaller than an atom, to a universe billions and billions of light years across. And it's still expanding.
I've often wondered how far future people will even know the Big Bang happened, because we know the Big Bang happened from watching all the galaxies fly away from us. Someday, the galaxies will be so far away from each other, it will be impossible to see anything else in the sky.
Scientists used to think the expanding universe was slowing down, but there was no way to prove it. Until they found double-star supernovas, Type 1As. They always explode when the white dwarf star reaches exactly 1.4 times the mass of our sun. And their explosions always release exactly the same amount of light. They are the perfect markers to measure distance in space.
Type 1A supernovae, when we know how bright they are and how bright they look, we can tell the distance. Because the farther away they are, the less bright they'll look at the telescope. And that has allowed us to accurately measure distances, not just to nearby galaxies, but to galaxies at the other end of the visible universe. Billions of light years. And that has allowed us to make incredible discoveries.
Astronomers thought they had found a way to prove the expansion rate of the universe was slowing down. What they got was a big surprise.
In 1998, astronomers made a remarkable and unexpected discovery. It was recognized that the universe, which should be slowing down because gravity, after all, is attractive, and the mass of objects should cause the expansion of the universe to slow down. But the expansion is speeding up. It's accelerating.
The constant light from Type 1A supernovas completely changed the way astronomers understand the universe.
Every science textbook on the Earth says that the universe is expanding and slowing down. Wrong. We now have to rewrite all the science textbooks on the planet Earth.
But astronomers still didn't know why the universe is expanding faster and faster. They began to think it's some kind of unknown energy. They called it dark energy, but it's difficult to prove because it can't be seen or touched or detected.
We really don't have a very good clue as to the physical nature and origin of dark energy. It's perhaps the #1 observationally motivated problem in all of physics right now, the nature of the dark energy.
From dark energy to black holes, supernovas have revealed some of the most profound mysteries of the universe. These exploding stars give us the building blocks of the universe and show us how it's all made. It's hard to imagine, but the atoms in our bodies today were made by a supernova billions of years ago.
The Bible says from dust to dust. Astronomers say from stardust to stardust. So supernovae are the key link in this cycle of life.
People think of space as being something very distant and very remote. It's light years away, hugely distant from us. That's completely wrong. Supernovae are right here. We are their children. They made us, literally, put us together.
We are star stuff. Without the supernovas, we could not exist. So when we walk around at night and we look up at the night sky and we see the stars and we feel somehow a part of them, the truth is we are. They are our parents.
Some scientists believe the age of supernovas could be ending. Smaller, slower burning stars, like our sun, will become more common, and giant stars become more rare. Supernovas have given us galaxies, solar systems, stars, and planets. They made us and everything we see. They are where destruction and creation meet. The destiny of the universe lies in the ashes of dying stars.